QCD. Just to mention that we
Okay. Okay. Yes. Okay. I should keep my time. So first of all, I'd like to thank the organizer for giving me opportunity and actually kind invitation to this workshop. So again, this is a lattice simulation talk, and the subject is slightly changed. I'd like to talk about the kind of finite density QCD using a lattice simulation. And my this is my main message. So we found the squared sound velocity normalized speed of light can be larger than 1/3. This is a value in the relativistic limit, free relativistic theory. Yeah, it is newly found by the lattice numerical simulation in the dense 2-color QCD. And this talk is based on the collaboration with Kei Ida-san in Kochi University and based on this paper. So, and let me start the why we studied 2-color QCD at the finite density region. So this is a general introduction. So this is a famous expected QCD diagram. So here we would like to consider, ideally, we would like to consider a finite density QCD. The Lagrangian is given by this equation. This is a standard QCD Lagrangian. And this is a number operator, and the associated coupling constant is a quark chemical potential mu. And in this QCD phase diagram, vertical axis is the temperature, and the horizontal axis is the baryon density, but it is proportional to the mu quark chemical potential. And as you know, lattice gauge theory is only known non-perturbative and gauge invariant regularization method. And as for the lattice Monte Carlo simulation, finite temperature at the 0 chemical potential region, this on the axis, lattice Monte Carlo simulation is available and it has been studied very well. However, in the other region, actually non-zero chemical potential region, Monte Carlo simulation failed because it suffered from the sign problem. I will explain this later. So, based on this situation, so we would like to consider that reduced model, so-called 2-color QCD. This is just a reduced model with a color degree of freedom in the real 3-color QCD. So we consider SU2 gauge theory with a fundamental fermions. And here in this slide, I'd like to explain, talk about the at least the 0 chemical potential region. This 2-color QCD has very similar property with the 3-color QCD. Actually, as you know, so at the 0 chemical potential region, standard QCD has these interesting non-perturbative or non-perturbative properties. And these qualitative property, 2-color QCD has the same property. And furthermore, here I'd like to say too much. Maybe as a quantitatively, for instance, equation of state as a function of the temperature shows a very similar, at least in the quantitative QCD, between the 2-color case, 2-color and the other color QCD. So actually, this is the plot of the trace anomaly normalized by the degree of freedom of the gluon. And so trace anomaly is given by the internal energy minus 3 pressure. And the horizontal axis is inverse of the temperature. And this is this shows a quark gluon plasma phase, so high temperature phase. And there is several dotted line. This is given by the Marco Panero by lattice numerical simulation. He investigated the SU3, SU4, 5, 6, 8 pair gauge theory. And so you can see these data overlap each other. So I think Marco Panero would like to say there is already NC equals 3 is a large NC. And here, cyan and red data show the result of SU2. And you see there are some discrepancy between the other and C. Mainly it comes from the different two-color QCD has a second order phase transition in the Quincy QCD, but the other NC has a first order phase transition. So around here is corresponded to the critical temperature. So here there are large discrepancy. However, naively speaking, qualitatively, two-color QCD also has a qualitative same behavior, and quantitatively, at most, the difference is at most a factor 1.3 or so. So here I'd like to say, at least qualitatively and hopefully, yeah, I'd like to say quantitatively, two-color QCD is a very similar property of the three-color QCD, at least mu equal 0. And at the mu equal non-zero, real QCD, we don't know anything. But in the case of two-color QCD, sign problem is absent even at the non-zero chemical potential region. I will explain later. So we can perform the numerical simulation in the case of two-color QCD, and we'd like to find the qualitatively and hopefully quantitative property of the real dense three-color QCD from this simulation. This is our basic strategy. And actually, we have several papers from 2020. So today I'd like to briefly introduce our result, first and second paper. So here, first one, we investigate the QCD phase diagram in two-color QCD using lattice simulation. And the second one is a collaboration with Yuya. So we gave some constraints on the two-color QCD phase diagram in two-color by using the Tofuft anomaly matching. And the main topic is based on this paper. So we investigate the velocity of sound using lattice simulation. Okay, so first of all, I'd like to talk about the what is sound velocity, and yeah, again, this is a QCD phase diagram. So in the case of three-color QCD in finite temperature, actually we have a finite temperature phase transition around 150 MeV, and this is a plot of the obtained lattice result of the equation of state as a function of temperature. And you see here is a critical temperature, and you see pressure and thermal energy, thermal entropy and internal energy monotonically increase in the in high temperature phase. And the corresponding sound velocity, actually sound velocity square is given by the del P over del E. And this quantity has a minimum around the TC. And in the QGP phase, it monotonically increases and finally approach to 1/3 in the ultra high temperature limit. This is a result of the hot QCD. And today we would like to consider what is happening in the finite density region. Actually, we would like to focus on the low temperature and high density region. And in the low density region, so this is a weakly interacting hadronic matter picture. So we can calculate some perturbative analysis. And in the ultra high density region, so in ultra high density region, quarks approach each other. So according to the asymptotic freedom, so quarks behaves like a free particle. So perturbative analysis is valid. So in the ultra high density region. So and it is expected plot of the sound velocity. So in low temperature, it grow up from 0. And in the ultra high density region, it is approached to the 1/3 again. So this is a value of the relativistic limit. But the problem is what is happening in the middle range of density. And actually, recently, it is a very important task to find the equation of state of the finite density QCD. Actually, recently, some experiment is ongoing. Actually, observation experiment is ongoing. For instance, neutron-neutron star merger or the gravitational wave. Or nicer, it is another observation experiment of the neutron star. And actually, equation of state of the finite density QCD can encode the mass and radius relation of the neutron star. So this is a one-to-one corresponding plot. So if the equation of states, pressure and internal energy has some first order phase transition in the middle range density, then MR relation has a cusp in the middle range of density. So it is weird. And another scenario, if we extrapolate this low density and high density region using the linear function, then corresponding MR relation has a waving behavior. And another scenario, if we interpolate this region using some smooth function, then in some case, corresponding MR relation shows this shape. So this shape means the radius of neutron star is almost independent of the mass. And this is somehow consistent with the observed data of the neutron star. And in this case, the sound velocity, corresponding sound velocity, this quantity has a peak, and the peak height exceeds the 1/3. This is one possible scenario. Actually, several phenomenological prediction has been proposed by the observed data or effective model analysis. Actually, the sound velocity has a peak in the middle range of the density region. And I think first proposal given by the Masuda-san, Hatsuda-san, Takatsuka-san 10 years ago. And they they actually proposed the scenario, quark-hadron crossover picture, which is consistent with observed neutron star MR relation. It suggests, this scenario suggests a square of sound velocity has a peak at the middle range of density region. And recently, Larry, McLaren, and Reddy also investigates the quark-ionic matter model. This is an effective model of the finite density QCD, and found again the sound velocity has a peak. And the most relevant paper for us, is given by the Kojo-san and Suenaga-san last year. They gave some microscopic interpretation of the origin of the peak, so-called quark saturation. But the most important point is that this mechanism works for any number of color. Actually, in the Kojo-san, Suenaga-san's paper, they investigate the effective model of the two-color dense QCD, and they show that it has a peak in the middle range of density. So this is a strong motivation. We investigate the sound velocity using a lattice numerical simulation. And this is also a general slide, but once we would like to perform the numerical simulation at low temperature and high density QCD, we have at least two serious problems. The first one is a sign problem. This is a famous one. Once we add the quark chemical potential term, then Euclidean action takes a complex value. So standard Monte Carlo simulation cannot be available. And however, here we avoid the sign problem. Once we reduce the color degree of freedom to 2-color QCD, then quarks is a fundamental representation of SUN gauge theory. So in the case of SU2 gauge theory, quarks becomes a pseudo-real representation. Then the sign problem is absent from the two-color QCD with even number of flavor. And the other serious problem is the so-called onset problem. It appears only in the low temperature and high density region. For instance, quark chemical potential is larger than half of pion mass or 1/3 of the nucleon mass. So beyond this threshold value, so pair creation because of this chemical potential emerge, then the calculation becomes unstable. And such instability comes from the actually phase transition from hadronic phase to the superfluid phase. And it is related with spontaneous symmetry breaking of the baryon symmetry. So to investigate such a spontaneous symmetry breaking of some symmetry, we usually add some explicit breaking term of the symmetry. For instance, Ising model case, so we add the external magnetic field, and in the case of chiral symmetry, we add the small mass, quark mass, and takes a massless limit. And in our case, explicit breaking term of the baryon symmetry can be given by this term, so-called diquark source term. Essentially, it is given by the psi bar minus psi. And the associated parameter is J. So we perform the numerical, actually Monte Carlo simulation with this action, QCD action, and the number operator with quark chemical potential, and the diquark operator with parameter equal J. Then hybrid Monte Carlo exact algorithm, hybrid Monte Carlo simulation are doable in the whole temperature and density region. This is our strategy. And today I will show you several plots, but the J0 extrapolation already taken in the old plot. Okay. So this is an introduction. And now I would like to show you our result. First of all, I'd like to show you the two-color QCD phase diagram. Actually, currently, there are several independent lattice groups, at least 3 independent lattice groups. So Simon Hans group and Russian group and our group. So different color denotes different collaboration result. And however, to my surprise, all data can be summarized by this plot, this picture. And first one surprising point is here. So actually, temperature is 100 MeV. Here we fix the scale Tc. A chiral phase transition is 200 MeV. Then around the 100 MeV, superfluid phase emerge here. So before our study, actually this study, it was expected superfluid phase emerge only in the extremely low temperature. However, even 100 MeV, this paper has solid evidence of the emergence of the superfluidity. So this is one solid result of this work. And the second one is given by the Furusawa-san and Yuya. And according to the two-fifth anomaly matching analysis, this is a purely analytical study. We obtained this constraint, confinement to deconfinement temperature is lower than the superfluid QG quark-gluon plasma phase transition. So this dotted line, dotted curve is lower than this solid curve. So, and this lattice simulation is consistent with this prediction given by the two-fifth anomaly matching. PEC. I will explain next slide. Yeah. Which one? QZP?
There's no one function.
Mhm.
Is the low temperature, low density phase separated from the QCD phase by a phase?
This one. In actual lattice numerical simulation, there is no center symmetry. So this is, I think this is a crossover line. Okay. And let me explain our phase diagram more detail. So here, now I'd like to fix the temperature, roughly speaking, 80 MeV, and investigate the phase structure in this line. So, and first of all, the order parameter of superfluidity is a dicoke condensate, QQ. So in the case of 2-color QCD, QQ is a color singlet particle. And here is our actual data. So QQ dicoke condensate is 0 before the this critical value of mu. And beyond this critical value, so QQ has a non-zero value. So, and monotonically increase as a function of mu. And this magenta line shows a prediction given by the chiral perturbation theory. So the scaling behavior is consistent with this prediction of the chiral perturbation theory. But anyway, this is this plot shows the emergence of the superfluidity. And Jeff's question. So in the superfluid phase, there are Bose-Einstein condensate phase and BCS phase. So, and this is a plot of the quark number density. And actually, the vertical axis normalized by the tree-level value. Actually, we can calculate the quark number density by using the free quark propagator. Then our data is in this region. It's consistent with unity. So in this region, free quark picture is valid in the superfluid phase. So we identify this region as a BCS phase, and the other region we identify Beck phase. And this green dotted line is a guiding line of the where Beck BCS crossover occur. So this is our definition. So anyway, summary. This is a summary. So at this temperature, we have hadronic phase, Beck phase, and BCS phase. So this is a summary. And now I'd like to show you our result of the equation of states. So to obtain the equation of states, we would like to know internal energy and pressure as a function of mu. And so we need at least two independent observable. And the first one is a trace anomaly. Trace anomaly is given by the beta function and the trace part of energy momentum tensor. And so the beta function, as for the beta function, we have 4 parameters in our Lagrangian. So first one is a gauge coupling constant. Here we denote the beta. And the second one is fermion mass. We denote it kappa because I'm lattice people. And the third one is mu, chemical potential. But the chemical potential is associated parameter of the number operator. And the number operator is non-renormalizable quantity, conserved quantity. So there is no renormalization for mu. And we also add the dicoke source term, associated parameter is J, but eventually we take the J0 limit, so this term can be 0. So essentially, we have to calculate the beta function of gauge coupling constant and the mass parameter, and essentially we have to measure the this one is actually F mu nu, and this one is essentially psi bar psi using the generated configuration. So this is a first step. And actually, we have to obtain these beta function non-perturbatively using the lattice simulation. And the third step is we obtain the pressure independently. So we can obtain the pressure by the numerical integration of the quark number operator I already showed our raw data in previous plot slide. So, and to be honest, so there are early works on the equation of state in the dense 2-color QCD by these people. However, they actually use the perturbative beta function here and here, because non-perturbative determination of the beta function is very tough work. Actually, we need roughly 3 years to obtain these two values. But anyway, we have done, and yeah, that is a new point actually. Anyway, so we utilize these value and measure this quantity. Finally, we obtain the trace anomaly and pressure respectively. And here, there I plotted the 3 data. So red one is first term of the trace anomaly. This one, coupling proportional to the beta function of the gauge coupling constant. And second term is described by the green data. And actually, green data come from the psi bar psi, and the psi bar psi actually is from the fermion loop. Then it gave a negative contribution to the trace anomaly. So in this plot, we flip the sign of the obtained quantity. So, and actually the sum of trace anomaly first term and second term is given by the red data minus green data. And in the hadronic phase, so red data is consistent with green one. So if we take the subtraction, then the total trace anomaly is consistent with 0 in hadronic phase. This is very reasonable because in hadronic phase is if we change the value of mu, the physical quantity does not change, so-called silver braid behavior phenomena. And in the Beck phase, red data is larger than green one. So red minus green data becomes positive in Beck phase. And in the BCS phase, red data is larger than green one. However, eventually green data is larger than red data. So trace anomaly in BCS phase is changed from the positive to negative. And it is natural because in the high density, fermion degree of freedom getting larger and larger, then fermion contribution also large. And blue data is a pressure. This is a monotonically increasing function, and it approaches to the this value, the value in the Stefan Boltzmann limit. Yeah, this is analytically obtained. And from the previous plot, finally, we can obtain the squared sound velocity, taking a ratio delta P over delta E. And again, sound velocity is consistent with 0 in hadronic phase, but it takes a non-zero value in the superfluid phase. And this blue curve is a prediction of the chiral perturbation theory given by the Son and Stefanov 2001. Actually, they investigate 3-color QCD with isospin chemical potential, a little bit different modified model of the real finite density QCD. But this equation has a no-free parameter once we fix the value of critical chemical potential. So, and our data is consistent with this prediction, chiral perturbation theory, at least in the Beck phase. And the chiral perturbation theory says eventually sound velocity goes to speed of light. So I think people believe at some point this chiral perturbation theory will fail. Actually, our lattice data far from this prediction in the high density region. However, here I'd like to stress our data of sound velocity exceeds this orange line. This is 1/3 the relativistic limit value. So this is our result. And let me explain what is new. So as I explained it, so far we know the finite temperature phase transition, and around the in the case of finite temperature QCD, so sound velocity has a minimum around TC and monotonically increase in the high temperature region. So the value of sound velocity always lower than 1/3. However, in at least the 2-2 flavor QCD at the finite density region, so sound velocity can be larger than 1/3. And it is previously unknown from any lattice calculation for the QCD-like theory. And actually, this is there is a famous bound, so-called holography bound or conformal limit given by Alex more than 10 years ago. And actually, I have to say, this paper is correct because this paper investigates finite temperature gauge theory, and they gave a bound. So sound velocity is smaller than 1/3. But they give a conjecture in the last sentence of the abstract. And so they gave a conjecture. It may be valid for the broad class of 4-dimensional theories. But here I have to say it is incorrect. So yeah, this is, but many people believe that this holography bound so far.
We knew that it's not right?
Yes. Okay, thank you.
Which class?
Yes. Yeah, actually, finite temperature and finite density is a quite different behavior. Yeah. Okay. And I think you would like to know what is happen further high density region. And actually, we have upper bound of chemical potential in the lattice numerical simulation. It comes from the mu in lattice unit should be smaller than 1. Otherwise, our numerical simulation data suffer from large discretization error. So this is the upper bound in our simulation. And to study the more high density region, so we have to perform the lighter mass simulation to make small, to obtain the small pion mass, or a final lattice simulation to keep this constraint. But both directions need expensive calculations, so we cannot do immediately. And so according to the perturbative QCD prediction, so people believe it is valid in the ultra high density region. So according to perturbative QCD analysis, sound velocity approach to 1/3 from below, then one minimum scenario is sound velocity is 0 in hadronic phase, and it increases and actually excess the relativistic bound, and it decreases once, and again it increases and approach to 1/3 in the ultra high density region. This is one possible simplest scenario. However, there is another expectation in the high density region. So once people he considered the power correction due to the Dicke gap in the superfluid phase, then a square sound velocity can be larger than 1/3 and approach to 1/3 from above. And Fujimoto-san and Fukushima-san, Kenji, also gave another prediction using the hard thermal loop resummation. And in this case, again, speed of sound approach to 1/3 from above. So still, it is an open question how square sound velocity approach to 1/3 from below or from above. So this is one open question. And So okay, this is a summary slide. Actually, we found the sound velocity exceeds the relativistic limit in finite density QCD-like theory. And one of the most important question is what is the mechanism of such a excess or peak structure of sound velocity? And according to the several effective model analysis, there are several scenarios Coke saturation given by the Kojo-san and Suenaga-san, and strong coupling with trace anomaly given by Larry and Kenji. And there are several scenarios. And now we investigate the actually hadronic force in the try to formulate the how to investigate the hadronic force in the superfluid phase. So at least the zero chemical potential region, we have a Lucia method or QCD method to investigate the hadronic force. And so we try to extend the QCD method into the finite density region. Actually, I have to say that the large sound velocity indicate the higher pressure as a function of energy. So, and the higher pressure might be induced repulsive force between the hadron. So this is a naive expectation. And here we would like to confirm that such a repulsive force between hadrons is emerged in the superfluid phase. But to be honest, in the case of two-color QCD, it is special because in the case of two-color QCD, all hadron, actually meson and baryon is a boson. So, and the bosonic theory has a repulsive force. Otherwise, vacuum collapse, decay, become unstable. So we believe that there is some repulsive force between the hadron in two-color QCD. So, but the most important question is such a mechanism is independent of the color degree of freedom. And this is a final plot. This is not my result. Actually, Bastian here gave a similar result. Actually, they working on the three-color QCD with isospin chemical potential, which is also another toy model of the real three-color QCD. And this case, sign problem is absent. And they show that even in this model, the sound velocity exceeds the 1/3 conformal bound by lattice numerical simulation. It is very promising and encourage us. So, okay, that is all. Thank you very much.
Questions? Very interesting stuff. So, in some of your thoughts, I saw that your lattice result began to disagree with parallel perturbation theory. It's just fairly early, right? Around
Good. Very good point. And actually, I skipped the detail of the phase diagram. You can see that this space. So this is corresponding to the here and the region. And actually, there is a thermal excitation of the quarks, actually hadrons. So this yeah. But this is, we'd like to say zero temperature, but it is low temperature, but not exactly zero. So yeah, yes, there is small thermal excitation. Yeah. Kenji's result. I'm sorry, I don't understand this result. I have some understanding this scenario, but yeah, so sorry. Please ask Kenji.
Thanks for that. One of the wild ideas, I guess, people had in the old days is that some density there will be a lattice of area, another like a crystal, and then I guess the sound waves will be crystal and break. I think one other such estimation is the sound in the crystal,
Crystal.
like a neutron crystal.
Actually, I don't, maybe I don't know the,
Yeah.
yeah. Mhm.
First part. Yeah, so I mean, what you're suggesting is that you have a large flexibility, right?
Uh-huh. Uh-huh. Okay.
Yeah, I think it exists somewhere at intermediate density, like you see this peak as intermediate.
Mhm.
But then at really high density, it will turn into dwarf matter. But maybe
Mhm. Yeah. Yeah.
This is reaching it. Yeah. Functional normalization. That's from the other side.
Mhm. Yeah. Sorry. Sorry, I don't know. But yeah, I remember you told me in the lattice conference, but sorry, I didn't check. I definitely will.
Right. So
Mm.
you're saying that when it's going up, we still have some trace of hadrons there. And then when it goes down, somehow we've associated it with quarks, the simple quark.
Yeah, actually, there are still unclear point because I didn't explain, but yeah, in the QCD phase diagram in Tukara, it is expected there are two BCS phase, so-called BCS phase with confinement. So I mean, this is a hadronic superfluid phase. And in the case of 3-color QCD, we believe that there is a quark-ionic superconductor phase. But in the case of 2-color QCD, actually the diquark is a singlet. So it is expected the confinement remain in the ultra high density region. So once we observe this local quantity, so-called the quark number density, so the value is consistent with a free quark picture. However, in the macroscopic scale, it is expected the confinement properties remained in the 2-color QCD. So I think it is another different point from the real 3-color QCD. Yeah, but it is still unknown. This blue region goes to the goes down or not. Yeah, this is an open question.
There are no more questions. Let's speak now.
Yeah.
Don't forget that 3:45